How will ocean currents impact Antarctic ice shelves? Hello, friends. Jim here. Well, ocean currents threaten to collapse Antarctic ice shelves, study finds. And here's a photo of the Dotson ice shelf found in the Amundsen Sea. A new study published in Nature Communications has revealed that the interplay between meandering ocean currents and the ocean floor induces upwelling velocity, transporting warm water to shallower depths. This mechanism contributes substantially to the melting of ice shelves in the Amundsen Sea of West Antarctica. These ice shelves are destabilizing rapidly and contributing to sea level rise. Led by Taiwook Park, the gentleman that took this photo, and Yoshihiro Nakayama, an international team of researchers from the Korea Polar Research Institute, Hokkaido University, and Seoul National University employed advanced ocean modeling techniques to investigate the underlying forces behind the rapid melting ice shelves. In a departure from prior assumptions linking ice shelf melting primarily to winds over the Southern Ocean, this study underscores the significant role played by the interactions between meandering ocean currents and the ocean floor in driving the melting process. Okay, I have to highlight this because finally, people are starting to understand it's the oceans, not so much the atmosphere. In a departure from prior assumptions linking ice shelf melting primarily to winds. Oh, what are the winds doing? That's got to be melting the ice shelves. No. The ice shelves are being melted from underneath. Yes, you have some warming of the atmosphere. Yes, you have some sun energy reaching down and melting from above. But when you consider how much heat water holds compared to air, there's a lot more, shall we say, this is a very scientific term, oomph behind that heat. The Pine Island and Thwaites ice shelves are among the fastest changing in Antarctica and are of particular interest due to their vulnerability in warming ocean waters. They act as massive barriers, restraining the glaciers behind them from galloping along into the ocean. However, their rapid melting potential collapse poses a significant threat to coastal communities worldwide because of the resulting rise in global sea levels. The study focused on the role of a layer of warm water beneath the frigid surface water known as the modified circumpolar deep water in melting these ice shelves from below. So now you're going to say, but if it's warmer, why is it under the cold water? Because isn't warmer water supposed to be less dense? Well, it has higher salinity. And because it has higher salinity, it makes that the salinity and the temperature taken overall makes it more dense than the very low saline, cold surface water. Similar to what we have in the Arctic Ocean, right? You have in the North Atlantic, Arctic Ocean, you have that very warm North Atlantic intermediate water, but it's very salty. So it sinks down to about 700, 1,000 meters and cruises right in through Fram, and then the heat diffuses underneath there and takes care of the sea ice. So it's similar, basically a similar situation. The intensity and trajectory of ocean currents encircling the ice shelves directly govern the influx of warm water. thereby intricately shaping their rate of melting. This shows the importance of the ocean in understanding and addressing the impacts of climate change. Yes, finally, ocean drive the climate, people. This shows the importance of the ocean in understanding and addressing the impacts of climate change. The researchers paid attention to the thermocline depth, which is the depth of the interface between warmer, deeper waters and cooler surface waters. Variations in thermocline depth significantly affect the influx of warm water toward the ice shelves. Until now, it has been believed that intensified westerly winds north of the Amundsen Sea propelled ocean currents along the shelf break, carrying warmer water toward ice shelf cavities. This phenomenon is particularly pronounced during El Nino events. Our findings challenge conventional wisdom, Nakayama says. Our study underscores that the interplay between meandering ocean currents and the ocean floor generates upwelling velocity, bringing warm water to shallower depths. Subsequently, this warm water reaches the ice-ocean interface, accelerating ice shelf melting. This internal oceanic process, driving ice shelf melting, introduces a novel concept. With this in mind, we have to reevaluate winds driving Antarctic ice loss, which can significantly impact future projections. In other words, you got to incorporate this new information, this new result, and modify the impact of the wind and assign more importance to the oceanic waters. Now, what is possible here is that the westerly wind could induce, coupled with the topography, could induce Ekman pumping that facilitates basically an upwelling, right? Ekman, that facilitates this warm water moving up to interact with the ice. So this is a very important finding. It shows you the role of the ocean. And basically, why is that water warmer to begin in the first place, right? Why do we have this modified circumpolar deep water, right? Ocean heat content. I know I sound like a skipping CD, but when the oceans have absorbed over 93% of our heat energy that we've introduced from burning fossil fuels, it's going to go somewhere and do something. This is one of those places. And for reference, I did a video discussing ocean heat content impacting Antarctic ice, land ice, as well as sea ice. Might want to check that out if you haven't done so already. So I am very appreciative of this study and of these findings. Until next time.